Awesome.
All right, welcome back. Yeah, our next speaker is Scott, who will tell us about quantum versions of the Karp-Lipton theorem. Please take it away.
Okay, great. So I have no grand vision to share with you today about the future of quantum complexity theory or whatever. I just have a little story to tell you that is close to my heart. This is a story that started about 20 years ago. So, some of what I'll talk about is old stuff, but it has a piece that was just supplied or corrected last year by Justin Yirka, who was my PhD student, just graduated last month. And it even has a couple pieces that I proved just yesterday as I was preparing this talk. So, but the real motivation for this talk is, will I shatter my own record for the most quantum complexity classes in one talk? All right. So, let's just start off the gate with, in the first slide. This is not going to be even close to all of them, by the way. Okay, but this is some of the setting where this talk is going to live. So on the left we have uniform complexity classes. Okay, P, BPP, BQP, and then we have QMA, quantum Merlin Arthur, and the subclass QCMA, which is where the witness has to be classical, but the verification of the witness can be by a quantum computer. And then QMA is contained in PP, which is sort of the counting class where you ask, do the majority of the paths of your non-deterministic Turing machine accept? Okay, in 2004, I gave a quantum characterization of PP. It is also equal to BQP with the ability to post-select on the outcome of a measurement, even if that outcome is exponentially unlikely. Okay, and then all that is contained in P space. Okay, now in the middle column, we have complexity classes with advice. Okay, so non-uniform classes. That's what the slash poly means. One way to think about advice is that it's just this string that can be chosen arbitrarily to help your algorithm, but it only can depend on the length of the input. Okay, not on anything else about it. Okay, another way to think of advice is that you are supplied a circuit. Okay, so instead of the Turing machine model, we're now in the circuit model, and the circuit can be a different circuit for each input length. Okay, so we have P/poly contains BPP, famous result of Edelman, and then you can have like non-uniform BQP, what you can do with any infinite family of polynomial-sized quantum circuits, and then you can really add the /poly to any of these classes. Okay, now one topic that I've been obsessed with, starting 22 years ago, is what happens when you add quantum advice that only makes sense for quantum complexity classes, of course, but you can have BQP/qpoly. My email address is bqpqpoly@gmail.com. I was amazed that it was available, but okay, but some of the basic results that I proved about quantum advice were simulation theorems, saying that you can take quantum advice and actually simulate it with classical advice at the cost of more computational power, in your complexity class. So I showed first that BQP with quantum advice is contained in PP with classical advice. Okay, that was in 2004, and then which in particular tells you that quantum advice is not infinitely powerful. Right? A priori, you could have imagined that a single quantum advice state, would just somehow unlock every possible input of size n. Right? That just by measuring it in the appropriate basis, it would just encode the answer, encode the entire truth table of an arbitrary Boolean function. Okay, but this shows that that's not the case. Of course, there are limitations on what you can learn about a quantum state by measuring it. Okay, and those limitations, they may give you more power. BQP with quantum advice may be larger than BQP with classical advice. But in any case, it's no larger than, say, post-BQP with classical advice. Okay, and now there are further results. You can combine witnesses and advice, right? So like QCMA/qpoly means you get quantum advice, which can be trusted, and you also get a classical witness, which can depend on the input, but which can't be trusted. Okay, so Andy Drucker and I proved in 2010 that actually these classes are even in QMA with classical advice. Okay, and then answering a question of Oded Regev in 2006, I studied what if you combine quantum witnesses and quantum advice, and even that can be simulated in P space with classical advice. Okay, so that's a rough lay of the land. You do have to be careful here. For example, if we studied post-BQP with quantum advice, that seems like a pretty natural thing, but it's very easy to see that that is literally the set of all languages. Okay, just because you can have a quantum state that encodes a superposition over your entire truth table of your Boolean function, and then you measure that state, you post-select on learning about the particular input X that you care about, right? So quantum advice can be weird in that way, okay? Okay, but now one of, arguably the most basic theorem that we know about in the classical world about the power of advice or about non-uniform complexity is the Karp-Lipton theorem, okay, from 1982. And you know that the Karp-Lipton theorem is important because there's a plaque about it right in the hall out there, okay, in the lobby of this building, and the display honoring Richard Karp, okay. And so basically, what this theorem says is that if NP is in P/poly, so like if NP complete problems have polynomial size circuits, even non-uniform ones, then the polynomial hierarchy collapses to the second level. Okay, that's what it says. So it sort of has a non-uniform hypothesis, but it has a uniform consequence. So what's the proof of this theorem? Well, it's very short. So this is here is the proof. A couple things to note about this photo, which is from 2006. One is that my hair is blonde and not gray, not yet graying. Okay, I'm wearing a sarong. This photo was taken in Daniel Gottesman's office for a now defunct website called the Sarong Theorem Archive, where each person proves a favorite theorem while wearing a sarong. Okay, but this is the complete proof of Karp-Lipton, right? That is easy enough to just reconstruct from memory. Okay, so how does it go, right? You say suppose that NP is in P/poly, so NP complete problems have polynomial size circuits. Then we want to collapse the polynomial hierarchy. So we want to show, let's say that it suffices for that to show that pi2 is contained in sigma 2, which means you can take any polynomial time predicate like of this form. For all x, there exists a y such that phi of x comma y holds, where phi is something, say a SAT instance, something computable in polynomial time. And now we need to give an equivalent formula, but where we switch the order of the quantifiers. Okay, so how do we do that? Well, we use the assumption that NP has small circuits. So with our first existential quantifier, we're going to guess the circuit for solving NP complete problems. Okay, and now we're going to use a further fact about NP, which is the equivalence of search and decision. Okay, if you have a circuit that can solve an NP complete decision problem, then we can also use it to actually find NP witnesses whenever they exist. So we'll assume that our circuit does that. And now we have the for all x from up here. And then we're going to just look at phi, but now we're going to use our circuit C to replace the existential quantifier over y, right? So we could just use our circuit to figure out what is the y that goes with that x. Okay, so hence, we've simulated pi2 and sigma2, which collapses all the higher levels of the hierarchy to that level. That's it. Okay, so what was the importance of this theorem for complexity theory? I mean, at the most obvious level, it was evidence that P/poly is not a ridiculously strong class, right? Like the question of whether NP is in P/poly is not is not the same as the P versus NP question necessarily, but it's also not completely different, right? It's, it can be connected somehow, right? And in fact, that there is a connection between the uniform and the non-uniform worlds of complexity theory. Karp-Lipton was also one of the first examples of the use of the polynomial hierarchy as a sort of yardstick of implausibility in complexity theory, where you say, if such and such is true, then the polynomial hierarchy collapses to the second level, the third level. I think the highest I've seen is the fourth level. I'm looking, I'm still awaiting the result where someone collapses it to the 17th level or whatever. Okay, but some people make fun of complexity theory by saying, it has a huge number of results of the form, if pigs could fly, then donkeys could whistle, right? But, they're thinking of things like Karp-Lipton, right? But this is useful, right? Once you just agree that the polynomial hierarchy seems to be infinite, then lots and lots of other things follow from that. And then finally, Karp-Lipton often shows up as an ingredient in other results. For example, in circuit lower bound results. Okay, so here's a good example. Okay, it is not hard to prove by just sort of a direct sort of diagonalization argument that the third level of the polynomial hierarchy does not have, let's say, linear size circuits. Okay, or in fact, it doesn't have circuits of size n to the k for any fixed constant k. Okay? That, by the way, that is different, much weaker from saying that it's not in P/poly, right? It's just saying there is no single polynomial size of circuit that can handle everything in the third level of pH. Basically, the way you can prove that is in the third level of pH, you can just explicitly say, I want to find the lexicographically first, truth table, on these inputs that has, that gives me a function with no small circuit, right? And we know that such a function must exist by Shannon's counting argument. Right, so then, there must be a lexicographically first one, such function, right, which is a single definite one, and in the third level of pH, you can express that. Okay, but then using Karp-Lipton, we can bootstrap from that. Okay, we can say actually the second level of the polynomial hierarchy cannot have circuits of size n to the k either. Okay, why not? Well, suppose it did. Okay, if it did, then certainly, NP would be in P/poly, right? Which means that because of Karp-Lipton, the polynomial hierarchy would collapse to the second level. So sigma 2 would equal sigma 3 anyway. Okay, so we already know that sigma 3 doesn't have the small circuit, so therefore neither does sigma 2. Okay, neat, right? Okay, so let's say that we try to prove a quantum version of the Karp-Lipton theorem. Like, what goes wrong? There's kind of an interesting thing that goes wrong here. Okay, let's say, let's suppose that NP was solvable, by a quantum algorithm using quantum advice, like NP is in BQP/qpoly. So then we might say, all right, well, now we have a quantum state to guess and not just a classical circuit. So the natural uniform class for guessing that would be not NP, but QMA, right? So let's try that. So in QMA, we can certainly guess an advice state, say psi sub n, that might, be usable for solving NP complete problems. Okay, but then, if I now want to use that state to collapse a hierarchy, the trouble is, like, I want to pass it. When I call an oracle, I want to pass the state to that oracle, have it pass the state to its oracle, and so forth. And the trouble is that, under our conventional notion of oracles, you just can't do that. You're not allowed to. Right? An oracle for QMA means I query with a classical string, which is an input, and I get back the answer to is that input in this language that is in QMA, right? Or, maybe PromiseQMA, okay? But I can't sort of pass a quantum state to my oracle unless it's a quantum oracle. So I seem stuck at that step, right? Once I've guessed the quantum state, then what do I do with it? Yeah.
Is there a reason why the quantum version is NP in BQ-poly and not QMA?
Oh yeah, good question. In this talk we will consider, if QMA is in BQP/qpoly, and that does give you more leverage. Okay, so that's one thing you could try, but notice that you still have the same issue here, right? That's not going to change this issue. Yeah.
Hierarchy you want to collapse?
Yeah, so we'll take what we can get. Whatever hierarchies are out there, we will try to collapse them and see if we succeed. Okay, so now this brings me to a paper that I wrote in 2006, which very stupidly I called "Oracles are subtle but not malicious." Like, I thought it was cute at the time, but the result was that no one actually knows what's in this paper. Okay, but the one result of this paper that is sort of better known, because it answered an old open problem of Lance Fortnow, is that I was able to construct an oracle relative to which all languages in the class PP have linear size circuits. And this required the polynomial method. It was, it was very delicate construction. But why did I care about that? Well, a year earlier, Vinod Chandran had given a really neat little argument, which I'll show you a version of it later, that says that PP has no circuits of size n to the k for any fixed k. Okay. So he used results on interactive proofs, or on the permanent to show this, and so so this was complemented the result that sigma 2 has no such circuits, right? And I was very curious: does his result relativize or not? Does it escape relativization? And so by showing that there is an oracle where this result is false, where PP has tiny circuits, it then implied that Vinod Chandran's result was somehow evading both the relativization and the natural proofs barriers. Okay, so it was then an example showing that both of these barriers could be circumvented in a single result, which then led to the question of, is there a third barrier to proving circuit lower bounds, which is part of what led me and Avi Wigderson to then come up with the algebraization barrier a couple years after that. Okay, but that's not what I'm going to talk about today. My jumping off point for the story that I want to tell you now is a different result from my oracles are subtle but not malicious paper from 2006. So I got interested in what lower bounds can we prove on quantum circuit size just unconditionally, right? Just no assumptions. Okay, and of course those bounds are going to be weak, compared to what we expect is true. But fine, whatever. Let's just see what is the best that current techniques can do. Okay, so a first thing that we can show is that x to the sharp p, so exponential time with an oracle for sharp p, is not in BQP/qpoly. So has no small quantum circuits even with quantum advice, and this is just unconditional. Okay, How do we prove that? You know, if you haven't seen how these sorts of things go, I'll run you through one. Okay, so you know, often in bounding the power of quantum advice, an extremely useful trick is to just guess the maximally mixed state in place of the quantum advice, right? If you don't know what the quantum advice is, you want to simulate it anyway, you just run your algorithm, but with the maximally mixed state in the advice register. Okay, here you know, I'm also assuming that we've done amplification, you know, to push down error probabilities so that they're very small. We can do that with just, you know, using like polynomially many copies of our advice state. And one nice thing that happens if you amplify, you push down your error probability, is that you can then take a quantum advice state and use it over and over again. Okay, you can reuse it. Okay, why is that? It's sometimes called the gentle measurement lemma or the almost as good as new lemma. Right, it basically says if you make a measurement on a quantum state, and if the outcome of that measurement could have been predicted almost with certainty, you know, given knowledge of the state, then you can implement that measurement so that it damages the state by very little. So you can keep reusing it. Okay, so we're going to use that fact. Okay, so we guess the maximally mixed state for amplified advice to our BQP/QPoly machine M. And then we're going to form the truth table of a Boolean function f that's supposed to be hard, that's supposed to not be in this class. How are we going to do it? We're just going to start at the top of the truth table and work down. Okay, and at each place, we're going to put whichever value, 0 or 1, cuts the probability that our machine accepts by at least half. Okay, so we're going to just take whichever is the less popular outcome, right? You know, having started with the maximally mixed state as our advice, right? So we make it less and less likely that, you know, having started with the maximally mixed state and then going down and computing this function, that we would get the right answer for each input, right? And so with each input, we cut the success probability by a factor of 2. But now we notice that that can't happen too many times. Once the success probability drops below 2 to the minus a polynomial in n, then actually there can't have been any valid advice state at all, right? Because if there was, then that advice state, you know, would have caused us to succeed with that probability, right? And, you know, it occurs in the maximally mixed state with this mass, right? So, you know, it had to be there if it with that mass, if it existed. Okay, and then the last observation is that all the requisite computations here to, you know, decide which output is less likely conditioned on all the previous outputs, those can all be done in x to the sharp p. So we get a specific Boolean function that's computable in this class, but that's not in that one. Make sense? Okay, and we can also scale that down. And we can say similarly, p to the sharp p has no quantum circuits of size n to the k for any fixed k. Okay, even with if we also throw in quantum advice of size n to the k. Right, so we can, you know, the same argument works, that we just scale it down by some exponential. Okay, so now, you know, just like what we did before, once we have some circuit lower bound, then we can bootstrap on it to try to get a better circuit lower bound, okay, by one of these sort of Karp-Lipton-like arguments, I'll say. Okay, so let me show you that. So now I claim that QMA exp, which is the exponential time analog of QMA, so, you know, a smaller class than x to the sharp p, I claim that this is also not in BQP/QPoly. Okay, so how do we show this? All right, you ready for it? I got the whole proof on one slide, okay, right here. All right, so let's go through, okay? All right, so let's suppose by contradiction that QMA has, you know, a small quantum circuit with quantum advice. All right, well then certainly p to the sharp p does also, because p to the sharp p is just sandwiched, you know. It's certainly a subclass of QMAX. Okay, now one example of a sharp p complete problem is the permanent, you know, of an n by n matrix. Okay, and the permanent has an extremely useful property in complexity theory, which is that it is self-checkable. Okay, which means if someone hands you a circuit for the permanent, then you can actually check in polynomial time. Okay, either that this circuit fails, or that it can be corrected to a circuit that computes the permanent on every input. Right. So, this is a famous result of Lund, Fortnow, Karloff, and Nissan. It was, sort of very, very closely related to, why there's an interactive proof for sharp P. So this was proven along the way to showing that IP equals P space. Okay, so this is like a crucial non-relativizing property of the permanent, right? Used over and over in complexity theory, and we're going to use it here. Okay, so what it means for us is that in QMA, we can just guess a quantum advice state for solving all problems in P to the sharp P, right? Which, we've, by hypothesis, that exists. And then we can verify that advice. We can check whether it really works, okay, by running this self-checking protocol or the interactive protocol. And what that gives us is that QMA equals P to the sharp P. Okay, and now we can just use the standard padding trick to translate this up by an exponential. We get that QMA x then equals x to the sharp P. Okay, but we already know that x to the sharp P does not have poly-sized quantum circuits, is not in BQP/qpoly. We proved that in the last slide. So therefore, QMA x doesn't either. Yeah. Okay, and similarly, you can also get that QCMA x is not even in BQP/poly, right? So like they're this class and this class have to match up in the sense that like you can guess, this class has to be able to guess this circuit, okay? But we also get that result. Okay, so then the next thing, after I realized this, 19 years ago, I said, let's scale this down to like get statements about say PP or QMA themselves. And how should we scale them down? Well, let's, in the classical world, that's done using Karp-Lipton. So let's try to prove a quantum version of the Karp-Lipton theorem. Okay, so here was my first quantum Karp-Lipton theorem. Okay, and here's what it says. It says, suppose that PP has polynomial sized quantum circuits, or equivalently that sharp P does. Okay, then the counting hierarchy, CH, collapses to QCMA. Okay, so what is the counting hierarchy? If you haven't seen it, it's just this. It's like the polynomial hierarchy, but starting from PP instead of from NP. Okay, so it's like PP and PP with PP oracle and PP with PP oracle with PP oracle and so on. Okay, a very interesting class, like above P to the sharp P, but below P space, okay, as far as anyone knows. Okay, and so now we'll also need one other important result from Fortnow and Rogers in 1998. Okay, and what they showed was that not only is BQP contained in PP, okay, but PP with BQP oracle is equal to PP, right? So the power of PP is not enhanced at all by giving it quantum computation as an oracle. Okay, so this is actually a very nice result, and you can give a different proof of it by using my result that PP equals post BQP. Right, you say, okay, if I have a post-selected quantum computer, then it just doesn't give me any more to have BQP as an oracle. Okay, so now let's prove this first quantum Karp-Lipton theorem. How's it go? We say, well, we get to assume that PP has a small quantum circuit. So in QCMA, we're going to guess that circuit. Right, natural thing to do. We get to guess, a poly-sized classical witness. Okay, and then we can turn that into a quantum circuit for computing the permanent. And then we can use the fact that the permanent is self-checkable. So now we can check whether our circuit works or doesn't work, or correct it into one that does work. Okay, and so now we have, let's say, a new circuit, a C prime that we know works. And then we're going to use that C prime to just sort of recursively unravel the counting hierarchy. right? So like if I had a problem in PP to the PP to the PP, then the first thing I do is I take that topmost PP and I simulate it by BQP, right? So I take the circuit, I sort of pass it through the oracles, so that all levels of the counting hierarchy now know this circuit, C prime, and then using that circuit, they can solve sharp P problems, right? So they can then, solving PP is then reduced to doing a quantum computation. So instead of PP to the PP, for example, you have PP to the BQP. Okay, but now Fortnow and Rogers tell us that PP to the BQP is just PP. So we've eliminated a layer of the hierarchy, and then we just keep doing that, starting at the top and working down. Yeah.
Here we're not using the quantumness of BQP at all, just that
Yeah.
we get a certain.
Yeah, I mean, like we're using this fact, right? I mean, like I will explicitly note when we are using anything about quantum in this talk, right? But like, yeah, we are pushing through, sort of beautiful known things in classical complexity theory, and then we're seeing what breaks. That's what we're doing. Yeah.
So here you assume that it does not do invalid queries, so it's not PromiseQMA.
Oh, yeah. Good. Well, okay. So PP is a syntactic complexity class, right? So it, so there's no difference really between PP and promise PP for this purpose. Later we will have to worry about promise classes.
I think the lowness doesn't work when it.
The what?
The lowness. Oh, the PP to the BQP is PP doesn't work.
Oh, yeah. Good. So yeah, we should say. I mean, this fact is true, but yeah, but it is moreover true that PP to the promise BQP equals PP. Yeah, I should have said that. Yes. Good. Okay, so now let's observe a corollary of that quantum Karp-Lipton theorem, and I will call this the quantum Vinay-Chandran's theorem. Okay, like I said, we're just gonna, try putting Q's in front of everything, and we'll keep doing that until something breaks. Okay, and then we'll see if we can fix it. Okay, so quantum Vinay-Chandran would say that for every fixed K, PP does not have quantum circuits of size n to the K. Okay? So how do we prove that? All right, well, let's, suppose the contrary. Right? Usually a good first step. Suppose PP has, circuits of size n to the K, so in particular, it's in BQP/poly. Then, by that quantum Karp-Lipton theorem, we know that collapses the counting hierarchy to QCMA, right? Now, PP and P to the short P, those are both sandwiched between QCMA and CH, so those come crashing down as well. These become equal to each other, okay? But now we're cooking, okay? Because we showed before that P to the short P does not have quantum circuits of size n to the K, and so therefore we now know neither does PP. Okay. All right. Now here's an even better result. Okay. While we're at it. Okay. PP does. I claim that for every fixed K, PP does not have quantum circuits of size n to the K, even with n to the K sized quantum advice. How can we do that? Well, let's suppose that it did. Okay. So suppose PP is in here, then PP is in BQP/qpoly. Then, by the self-checkability of the permanent, once again, in QMA, we could guess the advice state. We could use it to, make sure it works for the permanent, and then we could solve P to the sharp P. So P to the sharp P would equal QMA, okay? But we showed before that P to the sharp P does not have quantum, advised quantum circuits of any fixed polynomial size, and so therefore neither does QMA, and therefore neither does PP, which is in between QMA and P to the sharp P. Okay, notice we didn't even use quantum Karp-Lipton here. Okay, so that was sort of overkill for the purpose here. Okay, while I was preparing this talk yesterday, I realized that one can do something even better than that. Okay, so Rahul Santhanam in 2007 proved a really beautiful circuit lower bound. You know what? Maybe I won't go through this whole thing. Okay, but let me just tell you, Santhanam in 2007 was able to show that for every K, there is a language in PromiseQMA that does not have circuits of size n to the K. Okay, so he couldn't quite do it for MA. He could do it for, by the way, MA/1, MA with 1 bit of advice, okay? Or he can do it for PromiseMA, okay? And there's this, really neat argument based on padding, right? And that was the thing, even like beyond Vinachandran's result, this really provoked me into, coming up with the algebrization barrier. When, I heard Rahul give a talk about this at Stock 2007, okay? But I tried putting Q's in front of everything in Rahul's proof and seeing if anything broke, and nothing broke. Okay, so we get that PromiseQMA does not have quantum circuits of size n to the k for any fixed k, even with quantum advice. Okay, we get that consequence as well. Okay, but unfortunately, in my 2006 paper, I was a little bit too greedy. Okay, and I said, and clearly, right, and this is always where that there's a danger, lurking in a paper when someone says clearly, obviously, it can be seen that, whatever, right? Clearly, also, if PP is in BQP/QPoly, then the counting hierarchy should collapse to QMA, right? So we should also get that quantum Karp-Lipton theorem. Okay, and I sort of sketched the argument of how that would go. It was basically the same thing as before. If PP is in here, then there is a small quantum state that lets you solve the permanent once you know it. So in QMA we can then guess that state, call it psi. We can turn it into a state, a psi prime that is self-correctedly does the permanent. And then we just use that state to recursively unravel the whole counting hierarchy down to QMA, right? What's the problem, right? We've got the state. We just unravel everything, okay? And then I deduce this circuit lower bound as a corollary of that. Okay, so again, the corollary we can get anyway, right? I already showed you how to get the corollary without this. But this quantum Karp-Lipton statement, I later realized that this proof is just wrong, okay? And what is wrong about it? Well, I already indicated before what's wrong. What's wrong was that I was sort of implicitly assuming that once you know the quantum state, that sort of all the higher levels of the counting hierarchy have access to that state also, okay? And that is illegitimate, right? Like, if I'm QMA and I guess the state psi, then I have it at the bottommost layer. But how do I communicate my knowledge of that state to the higher levels that now need to be collapsed, right? So there's a problem in getting the recursion started. Okay, but fortunately, there is a result that can fix this. And my student, Andy Drucker, and I even proved that result in 2010, although we didn't realize at the time that this fixes this. Huh?
That is a question.
Oh, yeah, sure.
Yeah, I was just wondering, when you do this recursive unravel,
Yeah.
do you somehow need to worry that things get exponential, or like that?
Oh, no, you don't have to worry about that. And the reason is that there's a constant number of layers, right? In these hierarchies, right, we define them as like the union of all constant numbers of levels. And so as you unravel, the degree of the polynomial blows up and up, could get quite enormous, but it remains a polynomial. If you had a non-constant number of layers, then that wouldn't work. Okay, good. Good. So, okay, so now here is the result that we showed in 2010. And I already alluded to it at the beginning of the talk. But Drucker and I showed that BQP with quantum advice is actually contained in QMA with classical advice. Okay, so this was an improvement over my earlier result that said that BQP with quantum advice was contained in PP with classical advice. And this, like many surprising results, like this came about because, we were trying to prove it false. We were trying to show that relative to an oracle, this does not hold, because, how could it, right? And we again and again couldn't do that. And then we realized the reason why we couldn't is that it's true. Okay. In fact, we even showed something stronger than that. We showed that BQP/QPoly is equal to something called YQP*/poly. Okay, the Y stands for Yoda, if you want to know. Okay, I just needed someone other than Merlin to, and the star I'll tell you later. Okay, but basically, YP star is the class of languages that are decided by a polynomial time algorithm A with help from a polynomial size advice string, say W sub n, which depends only on the input length n, right? So just like in P/poly, you get this advice string that only depends on n. Okay, but now the advice string can no longer be trusted. Okay, it has to be verified, right? So you have a second polynomial time algorithm that exists to verify the advice. And we're told that for each n, there is at least one string that passes the verification, and that once it passes verification, then you can use it to decide membership of any x of length n. Okay, so this is also called an oblivious witness, right? But it's like a common, it's a subclass of P/poly, and it's also a subclass of NP. In fact, of NP intersect coNP. Okay, so you have this untrusted advice. Yeah, I don't trust Yoda. Okay, and then YQP star is the same thing, except that the algorithm can be quantum, and also the advice could be a quantum state. Okay, so and if you're wondering why the star, well, the way that we originally defined these classes, we said that the verification procedure can also depend on the input x. Okay, and I don't know whether that matters or not. With hindsight, I should have just defined the class this way. Okay, but because we didn't, now we have this annoying question of, are these two definitions the same? In any case, this is the one that we'll care about. Okay, so a slogan form to make it easier to understand what Drucker and I proved. Basically, what we said is that if you have trusted quantum advice, that's BQP/qpoly, that is equivalent to having trusted classical advice, /poly, plus untrusted quantum advice. That's YQP. So in other words, if you are willing to trust a classical advice string, then you don't have to trust quantum advice. You can use the classical advice to verify the quantum states for yourself. Okay, that's the surprising thing here. So for those of you who haven't seen this before, I have like this is a complicated result to prove, but I have a one slide, sort of sketch of how it goes. And sort of the key combinatorial insight that we needed that sort of, gave us the idea that unlocked this proof was something that we called the majority certificates lemma. Okay, so this might be of independent interest. So let me tell you what this says. It says, let S be any set of Boolean functions, F, each one mapping n input bits to one output bit. Okay, then we are interested in some particular function, f star in S, right? And we want to somehow specify it or like uniquely determine it. Okay, now we know that if I want to sort of specify f star by telling you what is its input-output behavior, I might need to specify an enormous number of input-output pairs. So for example, suppose that S consists of the all zeros function and also all the functions that are only one on a single input, right? Well then, no matter how many, I could show you an enormous number of inputs that the function is 0, and I still haven't specified the function within the set, right? Because I haven't, until I rule out every single place where a 1 could be hidden. Okay, but we show that something weaker and still very useful is true. Okay, we show that any f star in S can be represented as the majority of O of n functions in S. Okay, call those functions f1 up to fm, for m is O of n. Okay, and where each of these functions f sub I can be uniquely specified within S by listing its values on only log of the cardinality of S inputs. Okay, say like fi of x1 up to fi of xk, right? So each of these fi's is sort of isolatable within S by showing a small number of inputs and outputs. And then furthermore, if I take the majority of the fi's, I get f star. Okay? It's a fun exercise to try to prove that. You can use, sort of boosting, methods, sort of multiplicative weight updates kind of methods to prove this statement. And then what we did, Drucker and I, is we proved a version of this majority certificates lemma where sort of S is now a set of Boolean functions that are computable with a small quantum advice state as we vary that advice state. Okay, actually, technically they can be real valued functions because we have to look at the acceptance probabilities of quantum algorithms. Okay, but we prove a whole real valued generalization of this majority certificates lemma, using a bunch of results from computational learning theory. And then once we have that, then how can we take BQP/qpoly and simulate it by this YQP with classical advice? Well, the classical advice can uniquely specify, say, M functions, F1 up to Fm, such that their majority is the BQP/qpoly function that we wanted to compute. And also, our untrusted YQP advice can supply verifiable quantum advice states, say psi1 up to psi_m, where we can then verify those advice states using their input-output behavior that's listed in the /poly advice. And given these advice states, F1 up to Fm can be computed. Okay, so we sort of, in this roundabout way, we sort of give you a classical advice that tells you what quantum states to look for. That, if you see them and if they pass this test, then you can use them to compute F star. Okay, so now already in the 2010 paper, we realized that this YQP theorem could be used to prove a very interesting quantum Karp-Lipton theorem that we had no idea how to prove otherwise. Okay, so here's a result from our 2010 paper. I'll call it quantum Karp-Lipton version 2. Okay, it says, suppose that NP is in BQP/qpoly. Okay, so NP complete problems become easy with quantum advice. Then coNP to the NP, so the second level of the classical polynomial hierarchy, is contained in QMA to the PromiseQMA. Okay, so I don't quite get any one hierarchy to collapse, but I get something really strange to happen to uniform complexity classes that sort of smells like a polynomial hierarchy collapsing. Okay, we at least get that much. Okay, so how do we do that? All right. So certainly by our hypothesis and by the theorem that Andy and I proved, we know that NP is actually contained in YQP*/poly. Okay, and now our job is that we're given a predicate in pi2, right, which is coNP to the NP. So we have a predicate of the form, for every x, there exists a y such that phi of x comma y holds, where phi is, say, some Boolean formula, right? That's a pi2 complete predicate. Okay, and we want to decide that predicate in QMA to the PromiseQMA. So how do we do that? Well, first, we guess the classical advice string, call it W, for this YQP/poly procedure that exists. And we also guess a quantum advice state, call it psi, that would pass the check given W, that would pass the YQP check. And now we're going to call our PromiseQMA oracle. Okay, and we're going to hand off the W to that oracle. And then the oracle can again look for a state. Let's call that state psi prime that passes the YQP check. And now, now my oracle also, has this circuit for solving NP, right? Because it was handed the W, it guessed the quantum advice state, psi prime. And now the PromiseQMA machine is going to use that circuit for NP problems to fill in the Y quantifier, to find for each given X, to look for, does there exist a Y that makes this formula hold? Okay, so that is what we do. What is the key point here? The key point is that we never needed to pass the quantum state psi to the PromiseQMA oracle. Okay, why didn't we? Well, because we replaced, the quantum advice by classical advice, right? By this YQP/poly. Now there's just a classical string W, and you can pass that to the oracle, and then the oracle can reconstruct, because it's a PromiseQMA oracle, it can reconstruct the quantum state for itself. That's the key. Okay, so now what did Justin Yirka realize? Yeah, sorry.
Not sure I understand how YQP star is different from QMA poly.
Well, because the advice has to be verified. Okay, the advice cannot be trusted. That's the key difference. Okay, so YQP is a uniform complexity class. It's actually a subclass of QMA, right? Because the advice has to be verified. Okay, so it's like you can think of it as a QMA witness that is only allowed to depend on the input length. Okay, good. So that's the difference, right? Okay, so now last year, my former student, Justin Yirka, realized that he could also use my and Drucker's result, BQP/qpoly equals YQP*/poly in order to fix the quantum Karp-Lipton theorem that I wrongly claimed in 2006. Okay, so here is Justin's theorem. Suppose that PP is in BQP/qpoly, then the counting hierarchy does indeed collapse to PP, and in fact, even to YQP star. Okay, so how does he prove that? Well, by the hypothesis, we know that PP is in YQP*/poly. So, we can, in the lowest level of the counting hierarchy, we can just guess the, classical advice W to this machine. And then we can take that classical advice and pass it all the way up through the layers of the counting hierarchy, via oracle calls, right? And what it does is it allows, at each layer, it allows PP to be simulated in YQP star. Right, because it says, if you just guess this quantum circuit and then verify it, then you can now solve PP complete problems. Okay, but there's still one more difficulty. Okay, in order to make the whole counting hierarchy collapse, I need that PP to the YQP star equals PP. Okay, so the technical meat of Justin's result is that he proves this statement. Okay. The way that he proves that is by showing that YQP star is contained in another counting class that's called APP, okay, where it's a subclass of PP, or Lee in 1993 showed that PP to the APP equals PP. Okay, so by the way, APP also has a quantum characterization that was discovered in 2016. You can think of it as post-BQP, but with the restriction that the post-selection part can only depend on the length of the input. Okay, and then if the post-selection succeeds, then whether you accept or reject can depend on the input itself. All right, so while preparing this talk yesterday, I got another result that just goes through. Okay, there's a really beautiful result by Bischutti et al. From like 1994 or so. Okay, this is a thing that's worth knowing about, which actually improves over the Karp-Lipton theorem. Okay, it improves the collapse. What Bischutti et al. Showed was that if NP is contained in P/poly, then actually the polynomial hierarchy does not merely collapse to sigma 2, like to NP to the NP. It actually collapses to ZPP to the NP. ZPP being zero-error randomized algorithms. Okay, and the way that they proved that was very beautiful. Okay, it's again sort of boosting / multiplicative weights update. It's like you repeatedly use the NP oracle to sort of find better and better circuits for solving NP complete problems. You repeatedly, take your current guessed circuit and you sample random inputs on which that circuit fails, right? And then you look for a new circuit that also succeeds on those examples, right? So you sort of, you do this boosting trick, and then you take the majority among all the circuits that you found, right? And then once you have that circuit, then you can, for NP complete problems, then you can use that circuit to just unravel all the layers of the polynomial hierarchy. Right, and and then all of that is within your grasp, U being the ZPP to the NP machine. All right, so I checked that all of this also goes through. So if PromiseQCMA has small quantum circuits, then actually the whole QCMA hierarchy collapses to ZPP to the PromiseQCMA. So I'll spare you the details of that. Okay, but let me now summarize. So most of the story of the classical Karp-Lipton theorem and the associated circuit lower bounds can be successfully ported to quantum land. Okay, there is one repeated difficulty, which is that quantum states cannot be passed to classical oracles. Okay, but my theorem with Drucker that BQP with quantum advice equals YQP with classical advice helps a lot with that. Okay, a separate difficulty is that sometimes even when you have a uniform containment of quantum complexity classes, it doesn't really unravel a whole hierarchy the way that you want. So for example, we all know that if P equals NP, then the whole polynomial hierarchy comes, unravels down to P. Okay, but if you only knew that NP equals BQ, that NP is contained in BQP, then that might not happen. Okay. By the way, one problem that I believe is still open that I'd love to see solved is construct an oracle where NP is contained in BQP, but the polynomial hierarchy is infinite. Okay. Wait, is that known? I don't remember if that's known. I don't think it is.
It's still open.
Yeah, it's still open. Thank you, William. Yes. Yeah, we tried to tackle that.
That one's solved.
Oh, this one is solved?
No, what's open is an oracle where
Where NP is in BQP, but the
gate level.
but the exactly. So right. So show that like NP could be in BQP without the whole hierarchy then being in BQP. Yeah, good. Okay, so but certainly for collapsing whole hierarchies, it helps that PP to the BQP equals PP, and even PP to the YQP star equals PP. Right, so that helps us. All right, so let me mention a few open problems. One is like there have been papers by Garibian, Yirka, and others that explicitly defined and studied quantum versions of the polynomial hierarchy. Right, so that would be a very natural setting to study quantum Karp-Lipton theorems. I haven't really connected to that body of work. They, in that setting did show some quantum Karp-Lipton-like results. Like if P space is in BQP/qpoly, then this QC pi 2 equals QC sigma 2. So you get, this collapse. They also showed, by the way, that if QCMA has small quantum circuits, then the QC polynomial hierarchy collapses. Okay, but can one, relate the results that I showed to those results? If NP is in BQP/qpoly, does that literally collapse any hierarchy? I don't actually know. If PromiseQMA is in BQP/qpoly, does that collapse the QMA hierarchy? Okay, the main difficulty here is that famously for QMA, we do not know an equivalence between search and decision. For QCMA, we do. Okay, but for QMA, we don't. Like you could have an oracle for QMA decision problems, but it's not obvious if that helps you to actually prepare a QMA witness state. That may be harder. That may require a PP oracle. Right. So, and then you could say, what if we assume that there is a small quantum advice that lets you prepare QMA witness states? Like what, would that have weird consequences? Would that collapse any hierarchies? Yeah, I would love to resolve this issue about the definition of YP and YQP. And then, when you ask about like classical on the left side and quantum on the right side, then I don't really know how to get anything strange from, or I don't really know how to get circuit lower bounds in this scenario. Like how could we show that MAX does not have small quantum circuits? I don't even know how to get started there. I think, one would really need a new idea, even though that separation is presumably true with an enormous amount of room to spare. Okay. And there are also lots of general open problems about quantum advice that remain open. A well-known one is there a classical oracle relative to which BQP/qpoly is larger than BQP/poly? This is very closely related to the open problem of separating QMA from QCMA relative to a classical oracle. Greg Cooperberg and I gave quantum oracles that separate these classes, but the classical oracle case has resisted recent attacks. Can we give just a concrete candidate problem that is solvable with quantum advice, but not with classical advice? Very basic question. We have a candidate, which is Watrous' group membership problem, like checking membership in a finite black box group. You can do it with quantum advice, depending only on the group. We don't know how to do it with classical advice. There was a very recent breakthrough by Legal et al. That put a bunch of group theoretic problems in QCMA, but it's not clear that they have any implications for advice for BQP/poly. So often progress on this and on this go hand in hand, but this was a counterexample to that. And then I would just love to know for which complexity classes does adding quantum advice unlock all functions, all languages. Here are a couple cases that I don't know. So thanks for listening.
Any question for Scott? Yeah.
Yeah.
So I guess more broad there.
Yeah.
To ask, what are the connections between quantizing this quantum advice and shadow tomography or shadows? Like,
Yeah.
just-
So actually, the reason I invented shadow tomography in the first place came from thinking about quantum advice, right? So it came from, I had a result that it said that like, before the BQP/qpoly is in QMA/poly, I knew that it was contained in average case, like QMA/poly, right? And why was that? Because if you just specified a bunch of random here is the behavior of my function on a bunch of randomly chosen inputs, and then someone handed you a quantum advice state and it worked on those inputs, then for that very reason, it should work on most additional inputs for like reasons of the quantum Occam's razor theorem, which I proved in 2006. Right. And so then, the annoying, and that, so then that led me to that, paper on learnability of quantum states, right? This quantum Occam's razor thing. Okay. But then, I was annoyed that, okay, even then, all you would know would be that this advice state is useful for, deciding your language on most inputs drawn from this distribution. And so then I wondered, well, what if you wanted all inputs? Right. And okay, so clearly, like you can't get that like as given, but maybe if you change the question a little, right? Maybe if we said, look, here is a long list of measurements, like, and I am interested in, I have some quantum state in my head that has these behaviors on all of the measurements in this exponentially long list, right? Now, is there anything that I can specify to you, right? Such that there are several questions we could ask here, right? We could say, is there a classical string that I can specify to you where then once you find a quantum state, then that quantum state will be good for all of these measurements? We could also say, if you were given several copies of the true quantum state, then can you use those to determine the behavior of that state on all the measurements? Where now the fear is that as you start using them and measuring them, the measurements are going to destroy them and damage them. So you have to be super careful in how you measure them. That's what then led to my shadow tomography paper in 2018, right? But it all came out of thinking about quantum advice. Yeah, yeah, sure.
Any more questions?
It looks like, yeah.
Not sure, maybe I'm starting a new area in complexity theory.
Good.
But in crypto, we have this thing called auxiliary random oracle model and like related model. And, we have some crypto, but basically this is a model where you have a oracle access, normally random oracle, you just have oracle access to a truly random function. But here you're looking at the non-uniform version. You have in the pre-processing stage, you can compress random oracle to a polynomial string, like polynomial advice. But in the online stage, you still have oracle access to the random oracle. usually we have crypto application with complexity. You can ask, does it help you decide set or whatever, right? Yeah, it seems like it shouldn't, right? Why should access to a completely random function help you? But how do you prove it? So I was curious if you heard about it and what are complexity implications of this.
Yeah, I mean, it's an interesting question. I mean, I know that there are some results that say like things that you can do with a random oracle. You can often mock up the random oracle using the Nissan-Wigderson generator, for example, right? And get something that is just as good using that. So let me think. Like what's an example of a result of that kind where like all right, I'm blanking on it. I don't know. I'm happy to talk afterward about it. But yeah, we can. Yeah, I mean, certainly, I've been very, very interested in random oracles in complexity theory. In fact, one of my favorite open problems is, does P equal BQP relative to a random oracle, right? And Andres Ambayanis and I had this conjecture that would about influences in low degree polynomials, right? Or if it's true, then it says basically there is no hope of separating P from BQP relative to a random oracle. You would have to separate something in the unrelativized world in order to do that. But yeah, I mean, of course we study random oracles. If there's something different about your setting.
Yeah.
Okay, yeah, well, I'll be happy to talk about it afterward.
It looks like there is like, you can have like a field of stock folks in this. Yeah.
Maybe early CCC.
All right. Any more questions? If not, let's thank Scott again for the nice talk.
Thanks.
We are going into the lunch break, and we reconvene here at 2 p.m.
Good question. I mean, what is a weaker thing that you can? I mean, maybe there's something in between QMA and Karp. That's